All right, everyone. It looks like it's 11 o'clock, and I think we're going to get going here. Thank you, everyone, for attending. Again, this is our third official TigerStream webinar series. If this is your first time joining, TigerStream is a webinar series where we're trying to help get information out there about ongoing research that not only our research facility, the Stormwater Research Facility at Auburn University, is working on, but also anyone else who is researching and coming up with new things or just trying to share general stormwater information out there. So all of our webinars do get uploaded onto our webpage on YouTube, and you can find that going to www.youtube.com/@stormwater, and we'll be putting that link in the chat as well. But if you guys do have any questions during this webinar, please hit the Q&A button, as you cannot send any messages out directly, but we'll be happy to relay those questions to Brian, who is our presenter this month. But again, we'll get questions addressed at the end, but otherwise, I'll let Brian go ahead and introduce himself and we'll get it going.
Thank you, Janelle. So good morning, everyone. My name is Brian Roche. I'm a PhD student here at Auburn University in the Department of Civil Environmental Engineering. So I graduated with my master's here last December. So some of the work I'll be sharing today is work I did during my master's. Before then, I graduated from the University of Florida in 2021 with a bachelor's in civil engineering. So today we're going to be sharing some of the work I did as my master's on the performance evaluation of mulch berms in sediment applications. Just a quick overview of what we're going to go through. We're going to start with some background on erosion sediment control in general, then get into more sediment barrier and mulch information, as well as our literature review. Go through how we developed our large-scale testing methodology. Go into some testing that we did for Alabama Power, and then another set of testing we did on mulch berms to the Nebraska DOT. And then really want to make some comparisons between the information that we found out about mulch to other sediment barrier practices. Then go into some conclusions, recommendations for how we think this should get implemented, and kind of recommendations for future research as well. So start with the background. The US EPA identifies sediment as one of the most widespread pollutants that affect our waterways. And a major cause of this sediment pollution is from construction sites. Because on a construction site, when you remove that vegetation, grass, trees, bushes, stuff like that, that have once kept the soil in place, it's able to be washed away and have negative environmental impacts downstream. So uncontrolled sediment-laden runoff, such that they're a major threat to rivers, lakes, streams. They can increase turbidity, which can decrease the amount of sunlight that gets to vegetation. It can mess with fish spawning habits, as well as the sedimentation sitting at the bottom can actually reduce stream capacity, which can lead to increased flooding risk. So in Nebraska, so a lot of this work was from Nebraska DOT. Sediment's a major issue, with 83% of their lakes and 39% of their stream miles being impaired, which means they can't be used for their normal uses such as fishing, recreation, drinking water. And one major cause of impairment that they have is sediment from construction projects. So sediment barriers are kind of the last line of defense on a construction site. They're installed downstream of disturbed areas to remove some of the larger suspended sediment from sheet flow. Big thing that they do is facilitate settling and to a lesser extent filtration for most sediment barriers. Most common example of this is silt fence, but there are some alternatives such as wattles, mulch berms, stuff like that. Like I said, silt fence is the most common one. You've probably seen at least a few hundred feet of it even today. So it's just a geotextile, typically a plastic geotextile attached to posts and secured into the ground. And these posts can either be wood or metal, but a lot of these materials are not naturally occurring, so they have to be landfilled after use, and they produce a large amount of emissions during production. And a lot of times people aren't supposed to do this, but they'll get left on site and they can kind of break down, which could potentially lead to microplastic pollution down the line as that geotextile breaks down. So one alternative sediment barrier that we started getting interested in a couple years ago is mulch berms. So it's just a byproduct of land clearing, composed of shredded and chipped wood material, especially in a lot of areas where you're not able to burn. If you're clearing land, you're not able to burn this material. You have to mulch it. And a lot of places where have them trucked out to landfill. So yeah, these can be the mulch material can be formed in triangular or trapezoidal berms that can be used as sediment barriers. And a big kind of positive as compared to others is you can leave it on site after construction is completed. I would leave them in the burn shape or spread out with the dozer. And that could just remain on site and be allowed to decompose, unlike other non-natural sediment barriers. So we started to get used in Alabama. Alabama Power was a big, we really started getting interested in this material after they approached us and asked to do some testing. So they realized that on a single construction site, they were estimating about 100 truckloads of mulch a day, where they were having to pay to get truck off site and then landfill. So they began kind of putting these berms on their site as a way to kind of use that material so they didn't have to pay thousands of dollars to truck it off or put it in the landfill. But they still had to install other sediment barriers because it was not yet an approved practice. We've also seen it used on sites in Nebraska and some other jurisdictions, such as Minnesota, both sediment barrier and ditch check applications. And like I said, we're going to touch on, we also tested berms for a Nebraska Department of Transportation project on their sediment barrier practices. So like most research, to start with the literature review, kind of major findings are that many standard sediment barrier installations have not been evaluated for performance, and even much less, there's only a small amount of research that has been conducted on slash mulch berms, the performance of them through testing. And a lot of the laboratory testing that has been conducted has primarily been on conditions local to the southeastern United States. So we saw that there's three main varieties of testing. There's field monitoring, where you just, like I said, monitor a sediment barrier installation on an active construction project. Small scale testing, usually kind of typically in flumes. And then large scale testing, where you evaluate a representative section of a sediment barrier under controlled conditions. And each one of these has their takeaways, but also their limitations. So field monitoring, one of the big takeaways we saw from projects that were mostly looking at silt fence installations in the field, where that maintenance and preventing structural failure were kind of the key performance indicators. They found that there were, this project was for the Iowa DOT, and they found there were 4 failure modes: installation overtopping, an installation undercutting, flow being able to bypass the installation, and then excessive accumulation of material. So instead, each of these has their limitations. Kind of the big limitations of field monitoring are maintenance might not be consistent, inconsistent storm events, and then constantly shifting field conditions can make comparisons difficult. So small scale testing found it's really good to determine flow through rates and method of treatment. And they found that through most installations, most tested sediment barriers, sedimentation, which is when you have suspended sediments able to fall out of suspension within an impoundment and form upstream of the installation, was more of a factor of treatment than infiltration through the barrier. They also saw little to no testing on slash mulch at all through small scale. That's mostly wattles and silt fence materials. So this has more, you're able to have controlled conditions to this compared to field monitoring, but you can't test entire installations, only kind of little sections of it. So large scale testing tries to combine the positives of field monitoring and small scale testing by testing entire installations. One early method of this was rainfall simulation, but this doesn't really replicate field conditions because it's a very small representative drainage area compared to what you see in the field. But they did find that structural inefficiencies were a major component of performance. So to improve the state of large-scale testing, ASTM D7351 test method was developed to improve that. Flow rates could either be a set amount that's in the standard or calculated through local conditions, typically a 2-year, 24-hour storm event. This tests a 6.6-foot section of a sediment barrier. And kind of the big thing they wanted to look at was comparing upstream and downstream water quality. So this test method was used to evaluate a slash mulch berm installation. They used the peak 30 minutes of a 10-year, 6-hour storm event, and their material was between 1.5 inches and 0.03 inches, but I believe an average length of about 1/4 inch. They saw no structural failure occurring, but nothing was getting washed out or anything. It all stayed together. And they found that compared to straw bales, compost socks, and a silt fence installation that failed, they had a lower flow through rate and a lower discharge turbidity. So kind of they show that, okay, slash mulch berms can potentially be effective. So here in Auburn, we developed a large-scale sediment barrier testing methodology and apparatus based on that ASTM standard. But our big advantage of it is our test bed is 20 feet wide instead of that 6.6. So you're testing more of a representative section of that sediment barrier. In the past at Auburn, we tested standard and modified sediment barriers, typically under Alabama standards and conditions. And they saw, especially with silt fence, that the ability to impound at least 12 inches of stormwater facilitates 90% sediment capture upstream, which we'll get into a little bit once we go into our sediment barrier comparisons to Mulch Berms. So here is that testing apparatus. Flow is able to be introduced from supply pond into that equilibrium tank. Sediment is mixed with the flow during the mixing trough by hand. It runs down our 3-to-1 impervious slope into our test bed with the sediment barrier installed. So kind of summary of the literature review, we saw that large-scale testing combines the positives of both fluid monitoring and small-scale testing while reducing those limitations by ensuring they're able to test a representative section of the barrier under controlled conditions. We found that on other sediment barriers, treatment is mostly through sedimentation and the impoundment form by practices, with less happening through those installations. And that structural performance is a pertinent factor in the repeated performance. But we really saw that there was a clear lack of performance on Mulch Berms. So that's really what we wanted to get into and kind of see if the same results of testing that we saw from other sediment barriers can be the same for Mulch Berms. So from here, we developed our testing methodology. So all of our testing happened at our stormwater research facility, or if you're not familiar, it's about 12 acres out in Opelika, Alabama, dedicated to testing and training of erosion sediment control practices. And all the testing for this project was completed in our sediment barrier testing apparatus shown here. So because we did 2 sets of testing for Alabama and Nebraska, we had to determine our testing conditions for both. And we expected kind of wide differences to the variation of local conditions. It rains a heck of a lot more in Alabama normally than it does in Nebraska. So I'll just kind of walk through what we did for Nebraska, and the same thing, we followed the same process to get our flow and sediment introduction rates for Alabama as well. So we chose a representative drainage area based on their standards of about ½ an acre per 100 feet, or 100 feet of sediment barrier. And we were going to use the peak 30-minute of the average 2-year 24-hour storm. So that storm event is kind of what most sediment barriers are designed to withstand. And we use the TR55 urban hydrology for small watersheds method. So through this, we calculate our runoff depth from the curve number. See here in this map in Nebraska, which represents the infiltration characteristics of the soil. And then, so our rainfall depth using the Nebraska averages. From there, we got a runoff depth, which we used to create our design storm hydrograph. And all this resulted in, for the Nebraska conditions, an average flow rate of just under 0.09 cubic feet per second, and a peak flow rate of about 0.18 feet per second. And a total runoff volume in that peak 30 minutes of just over 1,100 gallons. So from here, we use these and other Nebraska average conditions. And the modified universal soil loss equation, which what this equation does is that it allows you to figure out the sediment yield from a single design storm event using local conditions. So we use that runoff volume, our peak discharge, our soil erodibility factor, which we took an average of the state of Nebraska, slope length and steepness factor of our representative drainage area, and our cover and practice factors were just 1.0 to represent a bare slope with nothing protecting it. So all this resulted in a soil loss of just under 0.4 tons from that 2-year 24-hour storm. Like I said, we repeated this process for the Alabama conditions, and we saw a wide variation. Nebraska had less than half the flow rate from Alabama, and about a third less sediment. So this really showed that we needed to test different conditions as different installations to perform differently in these widely different conditions. So here again is our testing apparatus. So like I said before, we pumped flow up from our supply pond into that equilibrium tank, where a system of valves and a monitoring tube were able to get our design flow rate. Sediment was introduced by hand into the mixing trough, and then the flow comes out of the mixing trough, now sediment-laden, down our 3-to-1 impervious slope, which has veins in there to facilitate sheet flow. That sheet flow then runs into our test bed where the sediment barrier has been installed. And then after it goes through the sediment barrier, it goes into our catch basin, which we can monitor the flow rate into based on a pressure transducer located at the bottom of the catch basin and the dimensions of the basin to figure out how to divert that depth, the change of depth over time slices into a flow through rate. So during testing, we took water quality samples at 4 locations, up on the impervious slope to get our kind of introduction flow rate. 2 places within the impoundment formed by the installation. S2 is at the top impoundment, S3 is the bottom. We did this to kind of see if there was water quality treatment occurring through sedimentation within the impoundment formed. And then S4 was at the discharge, so we can figure out what would be running downstream on a construction project. So we took these at regular intervals, every 5 minutes during that 30-minute introduction period. We had 5, 10, 15, 30, 60, and 90 minutes after that introduction period to kind of see how the system is dewatering. At the same intervals, we also took impoundment length and depth measurements as well. So we took these samples back to our lab and we analyzed them for turbidity and total spreaded solids according to ASTM standards. So to prepare our plot for testing, we used locally sourced soil. It's about 59% sand, 26% silt, 13% clay, which made a sandy loam. We leveled it with a screed and compacted in 2 lifts. This was our plot setup for our aub power berm, which was keyed in with a 6-inch cut down, sloping up downstream. For Nebraska DOT, we did not do a key at all. And then after we compacted our plot in 2 lifts, we laid plastic sheeting beneath the installation. As you can see here, that allowed for sediment that was deposited upstream to be removed and measured and compared to the amount that was introduced. We also installed the berm at the far end of the test bed instead of the middle. So we were able to capture the sediment that was passing into our collection tank. And from there, we were able to use a mass balance to determine percent capture within the berm by comparing what we introduced to what was captured upstream and what was captured downstream. And that kind of remaining bit was what was captured within the berm itself. So moving into our testing results, we're going to start with our aub power berm, which is 3 feet wide on top, 3 feet tall, and 6 feet wide at the base with that 6-inch key. So through these berms, we tested 3 of these installations 3 times each. We saw about a 75% reduction in turbidity through the berm, comparing the upstream and downstream sampling. We saw this was statistically significant. Kind of big takeaway of this is that these slash mulch berms might be performing a little differently than the other set of bears, such as silt fence and wattles, due to that kind of wider flow paths through, because we are actually seeing reduction in turbidity and sediment capture within the berm. So we saw an average discharge turbidity of 631 NTUs, and that was lower than the discharge we saw in previous projects testing silt fence and wattles under Alabama conditions. We did see fairly low impoundment with a maximum of 6 inches, but we did see a lot of sediment capture. So about 75% of sediment was captured upstream of the berm, a little bit less than we saw at other sediment barriers, kind of due to that lower impoundment formed. But we saw that, like I said, only 3.7% was reaching our catch basin. So that was about 22% of sediment was getting captured within the berm, leading to a very high sediment capture of the system overall. So after we completed this testing, we wrote the results in a report, which we passed on to Alabama Power, and they gave to ADEM. And it actually was able to get approved by ADEM for them to use on construction projects. So this is a clip from an article from Alabama News Center that they saved over $1 million on a single 4.5 mile transmission line right-of-way project. So I think stuff like this is one of the coolest things about our research group. It's cool being able to see our work get put into practice like kind of this quickly. Like even driving around, I've seen slash mulch berms on construction projects more frequently than I had before. We're moving on to our Nebraska DOT slash mulch berm. So this was part of a project where we tested basically all of the Nebraska Department of Transportation's commonly used sediment barrier practices. So here's their standard. They have a 2-foot minimum top, 2-foot minimum height, and a 5-foot minimum width. But a lot of their specifications recommend a 3-foot by 6. So the same dimensions as those Alabama power berms. And they had a material requirement you can see here with a maximum length not to exceed 20 inches and maximum width not to exceed 2 inches. So we made sure that the material we used fit the standards. So the aim of this project was to evaluate the standard mulch berm, modify it based on performance and testing, and then determine the most feasible and effective installation kind of recommend they can use, which you can see here. So we tested our first installation, our standard, under 3 back-to-back storm events. We then made modifications to that standard, which we'll get into in a little bit, tested those 3 times each. And then from those modifications, we identified that most feasible and effective installation based on cost, on how easy it is to install, and performance. And we tested that most feasible and effective installation, another 2 installations to generate more data for recommendations. So before we did this, we tested a control test to see, okay, how much sediment is actually captured just based on the change in slope as it's going across the test bed. So we saw with no installation present, we found a 67% sediment capture. So it was due to that flow velocity loss from the change in slope and as the flows make its way across the test bed. So here's kind of our standard berm in action. See here, relatively low impoundment, like under 3 inches on maximum. You can kind of tell here based on the high water mark there, that a lot of that material is not really being used for the flow going through it. It's kind of being used to keep the berm in place. But we did see that about 61% of sediment was deposited upstream, but only 1.9% of the introduced sediment was reaching the catch basin. So that's a total sediment capture of about 98.1%. So we saw about 38% was getting captured actually within the berm itself. So just like the Auburn power berm, we saw a high level of treatment and turbidity in total spent solids through the berm. We did, however, we were not able to take water samples of the bottom impoundment due to that lack of depth formed. But we saw a discharge turbidity of just under 2,000 NTUs, which was about a 93% reduction based on the upstream water quality for the turbidity. So after we tested this and we had a conversation with the Nebraska DOT, including a site visit on a highway project in Lincoln, we developed our first modification, which the goal was to increase performance while using less material, which we did through compacting the berm. So here's that looks like. It is a 3 feet tall installation. Sorry, 1.5 foot tall, 3 feet wide trapezoidal installation, compacted in 3 lifts using a jumping jack compactor. Typically, I think if you were installing a berm like this in the field and you're compacting, you'd run it over with a piece of equipment. We due to the walls of our testing apparatus, we weren't able to do that, so we used our jumping jack compactor instead. So here's that looked like in action. You can see that high water mark is a little bit higher compared to the first one. So we saw the 2 inches more maximum impoundment and a 17% lower flow through rate than the standard installation. It increased sediment capture only by a little bit to just under 99%, but more of that, 73.5% of that was upstream. With about 25 happened within the berm. So we saw lower discharge turbidity and TSS in the standard installation. So we did see that there was a difference between sample locations. So we did see that there was water quality treatment happening through sedimentation within the impoundment due to the water surface impoundment having a lower turbidity than the bottom of the impoundment. Like I said, and then we saw a lower discharge turbidity. So if we look at this over time, we saw a similar pattern to testing of other barriers with the lowest depth impoundments, so the bottom of the impoundment having the highest turbidity, with the water surface being less than that, and then the discharge being the lowest. But that relatively low difference between the top and bottom of the impoundment was due to the impoundment only being about 5 inches on maximum. But we also saw a similar pattern with our total spent solids as well. So we really wanted to compare these water quality results for back to our standard to kind of see statistically if it's better to compact than just pile up mulch. So we did see a statistically significant difference in the discharge turbidity and the total spent solids at a 95% confidence level. Do this analysis having a very low p-value. So after we tested this, we developed another modification. So with the goal of kind of increasing the flow path through the berm. This was a 12-inch tall, 6-foot wide berm compacted in 6-inch lifts. Like I said, we really wanted to see if we could lengthen that flow path through the berm and get more sediment capture in there and more water quality treatment through the berm itself. It showed very similar performance to that our first modification. Also, one thing I failed to mention earlier is after we tested and after we removed all the sediment, before taking out the soft water berm, we subjected these to what we called our kind of extreme case storm event, where we turned up our pumps as high as they could go, and basically to see if anything was going to wash out or any failures occurred. We didn't see overtopping or washout in either modifications. So this modification did slightly increase sediment capture upstream, only up to 78.2% though, and had very similar overall sediment capture to our other installations. So we did see lower discharge turbidity compared to that standard installation. We also did not see a statistically significant difference between the discharge water quality in our first modification, that kind of narrow one, compared to the longer one. So indicating that the longer flow paths likely did not really have an impact on water quality. So we also wanted to look at how much impoundment was being formed. So we saw each of the modifications increase impoundment, but we did end up selecting our first modification, which was that 1.5 foot tall by 3 foot wide compacted installation to be our most feasible and effective installation, because we saw that it increased impoundment, lowered discharge water quality while using far less material than the standard. So another thing we looked at, like I said before, was flow through rate into the catch basin. So we saw that it took about 3 or 4 minutes for flow. So this is for the most feasible and effective installation. So we saw that there's a filling period it took about 3 to 4 minutes for flow to start reaching the catch basin through the berm. And then it quickly rose to a steady maximum of about 0.06 cubic feet per second. Excuse me. And then dropping off after flow introduction starts. So our introduction flow rate was, like I said before, just under 0.09 CFS. So we did see a lower, so even at that maximum flow rate, we're seeing a lower than our introduction. So it's doing a good job of slowing the flow down and going through. Now I just want to make some comparisons between the performance of our slash mulch berms to other sediment barrier installations we tested for the Nebraska DOT. So here's kind of a chart showing our turbidity over time for silt fence, standard modified installations, slash mulch berms, and our straw and Excelsior wattles. So of these practices, our slash mulch berms had the lowest discharge turbidity. Even the standard, which is that orange circle with the dashes, that showed lower discharge turbidity than most of the other installations we tested, with our most feasible and effective slash mulch berm installation performing the best in discharge water quality. Kind of some of the big results that jumped out to us comparing was our sediment capture. So both our standard and our most feasible and effective slash mulch berm, despite having less upstream sediment capture due to that lack of impoundment formed, we saw that total sediment capture far outperformed even the most feasible and effective silt fence installation. So kind of a literature review. So our large-scale testing, which we found through a literature review to be the most effective way at evaluating sediment bearers. Our results indicate that slash mulch berms can be effective sediment bearers, especially compared to other installations. We also, one thing we looked at was previously conducted a life cycle analysis. I showed that far less emissions are produced. A study earlier found that 78% less kilograms of CO2 equivalent are produced in the production of a slash mulch berm compared to a Georgia DOT type A silt fence, and 90% less than type C silt fence. In Alabama Power, they found that there was a far lower cost of installation, maintenance, and removal compared to silt fence, with about $20 per foot of silt fence versus $3 a foot for slash mulch berms. Kind of widely due to you're not having to landfill the silt fence, you're not having to remove this, you're not having to remove, landfill will remove the slash mulch berms. You can just leave it on site to decompose. So based on our results, some of our recommendations for how this research can be implemented, we really recommend the slash mulch berms to be used when feasible, because we saw higher performance compared to other sediment barriers, as well as it being more environmentally friendly, as you're able to just leave it on site and it does not have to go into a landfill, and there's no emissions, not as many emissions associated with production of it. What we really saw was dependent on material availability. Like, in our conversations with the people from Nebraska DOT, they love to use it, but a lot of their construction sites are not wooded, so they don't have the material use. We really saw that compaction is also key for performance. We saw that statistically significant difference in discharge water quality produced by using less material due to that compaction. Like I said, we can also use less material than most standards include. It doesn't need to be 3 feet by 6 feet. It can be 1.5 feet by 3 feet and get higher performance due to that compaction. Some other research that I think could be useful in kind of determining more uses for slash mulch berms. I'd love to see some longevity testing to kind of ensure usability on some projects that might take longer, as well as testing of different materials to see if like wood type and gradation differences might have a role in performance. And then I'd like to see kind of in mulch and other applications that I've seen slash mulch be used in, such as ditch checks and slope protection. So with that, if there's any questions, I'd be happy to answer. I probably went a little too quick, so I'll have plenty of time for questions.
It looks like we have one question asking if there's a link for the report for the Nebraska DOT research.
Yes, there is. Our final report, I think, should be published somewhere. We can get you that link. I probably have to search a second for it, but I think there is a link on Nebraska DOT. Dr. Perez, you have a better answer for that. I think if you go on Google Scholar and search Nebraska DOT sediment barrier, you can potentially find that link. Dr. Perez just sent the link in response for the report.
Yeah, thanks, Brian. Yeah, I just posted a link there. You can get it directly, yeah.
I know we moved a little fast on this one. Do we have any other questions, though? What was the age of the wood used?
I believe it was only a couple of months, so we got it delivered by the Auburn Power donated mulch for both the use of for testing for theirs and testing for the Nebraska DOT. So we ended up having a stockpile on site that probably sat for like at most just a couple months before we use it for testing.
Has there been any research as to how much material is created relative to the wood area cleared per acre?
Not that I know of, but I'd be very interested in seeing research like that. It seemed like Alabama Power was on their right-of-way projects was using like as much mulch as they were producing. It sounded like they were producing 100 truckloads a day of mulch. I'm not sure what the size of that project was that they looked into.
Have you considered using any polymers on the surface?
We have not. That would be probably would be effective in kind of reducing the turbidity further. So I'd be very interested in seeing future research on testing with that, especially with that water quality.
Was the wood fibers used of fines prior, or did you use chips as provided?
So we just used the chips as provided. So there likely were some fines in there. Like I said, we made sure to follow the Nebraska DOT specifications, which only really had a maximum size, not necessarily a minimum. So there likely were some fines in there.
While people are thinking of any other questions that they might have, if you're still with us and you're needing to head out a little early, I just want to go ahead and say thank you for joining. Additionally, with our TigerStream here, anyone who is interested in speaking or knows anyone who might want to speak, please feel free to reach out to us and we'd be happy to add you to the list and get you on here so that you can present and share your work, whatever that might be. Otherwise, if you have any other questions, if you think of anything outside of this hour, you're welcome to email us and we will be happy to get those questions answered directly as well. For For anyone who needs PDH hours, there should be an automated email in the next couple of days that will contain the necessary information so that you can get that filled out as well. Next month, we will have our other PhD student, Grace Kerr. She'll be giving a presentation about her master's work. She's a new member of our research group and we're really excited to have her. And so if you're wanting to attend, she's thinking about presenting on utilizing acid mine drainage sludge in reclamation. So please keep your eyes peeled for that announcement as well. Since I'm not seeing any other questions, I think we're probably good to call it. So again, if you have any other, oh, we have one more. Okay, you got a comment saying, "Good job, as well presented, Brian."
Oh, thank you, thank you.
Thank you everyone again for joining. And if you do think of anything, please feel free to reach out, and we're happy to get you answered.
Thank you, Janelle.
Thank you, Brian.